So let us start. We've been looking at algebraic structures. So we've looked at groups. We've also looked at rings. So we want to now look at fields. We exhausted the rings and groups. Of course, all these things are related. Only the difference between them is not much. Once you know what groups are, and how to do operations in groups, and then it becomes easy for us to do even with the rings and also with the fields. So I've said that a field is a very important concept in algebra, abstract algebra, and it represents a set that is equipped with the two binary operations. So the binary operations would be that of addition and then multiplication. So this set would be equipped with both two operations. This is different from the way the group was, because the group, we had those two operations, but that set would be a group either under addition or under multiplication. So we were to separate. We're not having those two operations at the same time, with the set with the two operations at the same time. We're considering one operation at a time. But when it comes to this field, we're considering the two operations at the same time. The two operations are supposed to be considered at the same time, not one at a time. So that is, I've said a field is a set, and you can see my set here, F, has been equipped with the two operations. You can see this addition, and you can see that this is a multiplication. So the two operations at once. So let me define. A field is a set F together with these two operations that we call addition and multiplication. And this field, together these two operations, these two operations then must fulfill some conditions. And those conditions, we've already looked at them while we were looking at groups. We're looking at closure, looking at associativity, commutativity, and so on. So you're saying that a field must have these two operations, and these two operations, one must be closed. For instance, under addition, the set F, which we are referring to as a field, must be closed. That means you pick any two elements from the field, pick any two elements A and B, their sum must be in F. So if you pick any two elements from F, their sum must be in F. So we say, therefore, this F is closed under addition. And of course, under multiplication, you only need to subtract 0 from F, so that we are now considering F with a star, F without 0. So we also say that if F is to be a field, we've said 1 must be closed under addition, and 2, it must also be closed under multiplication. When you just remove 0 from it, it must be closed under multiplication. Pick any two elements from F, their product must be in F. That's what it means. So that is the first axiom, that F must fulfill for it to be a field. That 1, it must be closed under addition, and at the same time, it must be closed under multiplication. Now, after that, we have other axioms. Those are not the only axioms. The other ones are here. It must be associative under addition, and it must also be associative under multiplication. So F to be a field, again, it must be associative under addition and associative under multiplication. That means under addition, what it means by associative, it means you pick any 3 elements from F and sum those 3 elements. If the bracket is here, the result must be the same as if the bracket changed the position and came here. The result must be the same. Under addition, that must be satisfied. Then under multiplication, again, you pick any 3 elements and B from F, ABC from F, their product, these two products must be equal. Just change the position of the bracket. And that is what we call associativity. So we say F, if F is to be a field, then it must be associative, both under addition and under multiplication. So you're saying that these two operations of addition and multiplication, we are moving with them every axiom. We check every axiom if the two operations satisfy that axiom. So the other axiom that we look at is that of commutativity. Under addition, you pick any two elements and see whether the sum of A plus B is the same as this B plus A. That is, if you pick that, we want to see if that will be correct. We want to see whether 3 plus 4 will be the same as 4 plus 3. It's not always the case. It's not always the case. But if it happens to be true, then we say that F is commutative and addition. What about other multiplication? You pick any two elements A and B, their product, A times B should be the same as B times A. And then we say that F is commutative under multiplication. So what we are saying is F must be commutative both under addition and multiplication. And then we have the identity element. We're saying that for F to be a field, again, it must have both the additive identity and the multiplicative identity elements. The additive identity element is 0, so it must contain 0. And it must also contain the multiplicative identity element, 1. And these two identity elements should not be equal. Those two identity elements should not be equal. So it must contain the additive identity element, and it must also contain the multiplicative identity element. And the two identity elements should not be equal. So that is another property that it must fulfill. Then again, every element must have an inverse. Every element that is, if you have consider A, then A under addition must have an inverse. I must have an additive. Every element must have an additive inverse and a multiplicative inverse at the same time. So it must have an additive identity element and a multiplicative identity. Every element should have those two identity elements. An identity for addition and the identity, not identity, inverse. Inverse. It must have, every element should have those inverses. It should have the inverse for addition and it should have the inverse for multiplication. Every element. So we're looking at examples. And of course, when we begin looking at examples, you will see that for it to be a field, and then it must fulfill all those properties. And we are considering two operations at the same time. What about distributivity? Distributivity is just one, so it has both operations at the same time. So we don't need to have two properties here. It's just one property for addition, and it has both addition and multiplication at the same time. You can see this multiplication and this addition. This multiplication and this addition and that multiplication. This is what we call distributivity. Now, so let me just ask a question here so that we are familiar with what we are doing. Want to check whether this is a field. Want to check whether the set of integers is a field. What I mean by set of integers, I mean elements, -4, for instance, -3, -2, -1, 0, 1, 2, 3, and so on. So the question is this a field? And for us to answer this question, we want to see whether it fulfills the axioms we've looked at with the two operations. So one, for instance, want to see whether it's closed under addition. Want to see whether it's closed under addition. want to see whether it's closed under addition, and at the same time, we want to see whether it's also closed under multiplication. Now you can see what we mean by closed under addition. Of course, we mean that pick any two elements A and B, their sum must be in Z. So that is possible here. You can see if I pick 1 plus 2, if I pick 1 plus 2, for instance, you can see the answer is 3, which is in Z. So this set is closed under addition. What about closure under multiplication? For instance, 2 times 3 would be 6. And you can see 6 is a member of this set. So this set is closed under addition and closed under multiplication. So we then proceeded to another property and see whether it fulfills. Of course, when you go to associativity, it will fulfill that. If you go to identity element, you can see it will fulfill that it has the identity element of an additive identity element, and it has the multiplicative identity element. So it fulfills that. But where it fails is the inverses. Where it fails are the inverses, because you can see it has the additive inverses. It has the additive inverses. For instance, 2 has an inverse -2. -4 has an inverse, which is 4. But it fails to have multiplicative inverses. It fails to have multiplicative inverses. For instance, I cannot see an element which, when multiplied by 2, gives me 1. I cannot see that element. That element is supposed to be the inverse of 2. That element which, when multiplied by 2, gives you 1, is supposed to be the inverse of 2, but I cannot see it here. I also cannot see an element which, when multiplied by -3, gives you 1. I cannot see that element here. So it means the set of integers, therefore, is not a field. The set of integers, therefore, is not a field. And you've seen how we've looked at it. We only required one property that it cannot fulfill, and we've seen that it cannot fulfill the property of inverses. Under multiplication, we failed to see the inverses. And of course, we said for it to be a field, the two properties, the two operations are considered at the same time. So you consider addition, then consider multiplication. So this is the beauty of a field. So you can see how a field is different from rings and different from groups. Now, so I wanted to look at other examples, and I can see I've said that the rational numbers are fields. Rational numbers are fields. Let me just remind you what the rational numbers are. Rational numbers are numbers that can be written in the form A out of B, where B is not equal to 0, and the GCD of A and B is 1. The GCD of A and B is 1. In other words, the only common factor between A and B is 1. This is what we call rational numbers. Let me give you examples of rational numbers before we say that they form fields. An example of rational number, this is a rational number. This is a rational number. This is a rational number, because it can be written as 7 out of 1. Even this is a rational number. Even this is a rational number. Even -7 is a rational number. So what I'm saying is, all the whole numbers you know are rational numbers, so whether positive or negative. All the whole numbers you know. You can see this whole number, this whole number. Even this is a whole number. Even this is a whole number. These are, all of them, all whole numbers, negative or positive, are rational numbers. Even 0 is a rational number. And of course, all fractions that we know, negative or positive, are also rational numbers. So long as the common factor between the two, the numerator and the denominator, is 1. So long as the common factor between the numerator and the denominator is 1, that fraction is a rational number. So when you look at those numbers, then you see that they form a field. Because when you talk of closure, for instance, if you take a number like 9 and multiply by 3, we expect 27, and 27 is a rational number. You take a number like a 9th times 7, you expect to get 7 out of 9, and 7 out of 9 is a rational number. So anything you do, and in fact, let's add a half plus 2/3. No, okay, let me say a third plus 2/3. This is 1, which is a rational number. So you can see closure. You can see closure here. You're seeing closure. What I'm referring to is closure here. A half plus a third. The LCM will be 6, and that will be 5. And this is a rational number. So you add any two rational numbers here, you're getting sum that is a rational number. You multiply any two rational numbers, you get a product that is rational. So we then say that they are closed under addition and closed under multiplication. Of course, associativity will be obvious. Associativity will be obvious. Let's look at the identity element. It has the identity element under multiplication, addition. The additive identity element is 0, is a rational number. And then the multiplicative identity element is also there. So it has that property fulfilled. The other property is that of inverses. We want to see whether the additive inverses are there for the same element, and the same element has a multiplicative inverse. Let's take this, for instance, 9. I picked 9. The additive inverse, it is a member here. -9 is the additive inverse. What about the multiplicative inverse? Is a 9th, and is there. A 9th is in this set. -9 is also in this set. And you realize that every element would have an additive inverse and a multiplicative inverse. All other properties will be satisfied. So that is why we then say that the set of rational numbers forms a field. Forms a field. So you need to know what a field is. That's why I'm giving these examples. You need to know what a field is. You need to know what a group is. And of course, those ones you know. So if you're given a set, you should be able to tell, because we have sets which are both groups, there are also rings and there are also fields. Like this set of rational numbers forms a group, forms a ring, and now forms a field. We saw in our first example, the set of integers. The set of integers, this one we know, it forms groups, but it has failed to form a ring. No, it has failed to form a field. It has not formed a field. So you have sets that will form both groups and fields at the same time. And you have those that can fail to do that. But the good thing is that we need to know what is a field and what is. So again, the real numbers who form fields, even the complex numbers. What are complex numbers? Complex numbers are numbers that can be written in the form a plus ib, where I is imaginary. Where I is imaginary and has the property that its square is -1. The property of I I has the property that its square is -1. So what I mean, therefore, numbers like 3 plus 4i, this is a complex number. Numbers like -3 plus 7i. Numbers like 20 minus 3i. Any number combined with another number that has an I is a complex number. Even numbers like 7 are complex numbers because 7 can be written as 7 plus 0i. So 7 becomes a complex number. Even -7 is a complex number because it can be written as -7 plus 0i. Even -1,000 is a complex number. It can be written as -1,000 plus 0i. Even a half is a complex number. Even -15, let me say -7 out of 15. So therefore, complex numbers are bigger than the real numbers and they're bigger than the rational numbers because all the rational numbers are contained inside these complex numbers. What I mean is all the fractions you know are complex numbers, whether negative or positive. All the whole numbers you know are also complex numbers, whether positive or negative. And to add on that, all other numbers that can be written in this form are also complex numbers. So let's check whether they are closed. So let me pick this complex number and pick this complex number. If I add these two, I'll get -5, which is also a complex number. Okay, let me now multiply these two. I'll get +6, which is also a complex number. Okay, somebody else might be wondering, what about those which have I? Let me again multiply those ones and add them and see whether they're complex numbers. Let me begin by adding because that is easy. I want to pick this complex number, 3 plus 4i. And I want to add to it another complex number, 7 plus 2i. What do I get? I add the like terms, and that gives me 10. 3 plus 7, that gives me 10. And this will give me 6i. And this is a complex number. What about their product? 3 plus 4i multiplied by 7 plus 2i. 3 times 7 will be 21. 3 times 2i will be 6i. 4i times 7 will be 28i. And then 4i times 2i will be -8. -8. And then you collect like terms. 21 minus 8 will be 13. And then 6i plus 28i will be 34i. And this is a complex number. Now, those who didn't see how I got this -8, what I did was 4i times 2i gave me 8i square. And we had already said that I has the property that I square is -1. We had already said that. So this becomes 8 times -1, which is -8. That's how I got that. Now, but what is important here, we've seen that complex numbers are closed under addition and they're closed under multiplication. And so you may want to check whether they have identity element under the additive identity element, and you can see 0 is there. 0 is a complex number. And the multiplicative identity element is also present because 1 is a complex number. Every complex number has an additive inverse, the multiplicative inverse. For instance, let me take this complex number. Let me take this complex number, 3. Its additive inverse is -3, which is a complex number, and its multiplicative inverse is a 3rd, which is also a complex number. So therefore, the set of complex numbers forms a field. Set of complex numbers forms a field. So I now believe that we all know what a field is. If you're given some set and you're asked whether it's a field or not, you should be able to tell whether it's a field or not. Now, having known that, what is more interesting to us in terms of security is what we call the finite fields. The finite fields is what is now important in terms of security. What are they? These are fields mod n, but we are very much interested in mod p, where p is a prime number. We are very much interested with the prime numbers here. We will have said mod n, but we want just to go straight to what we are interested in, and that is when p is a prime number. So we then get a finite field. We are saying that for prime number p, the set of integers 0 up to p minus 1 under modular arithmetic forms a finite field. So we can denote it this way, or we may want to denote it this way. Want to denote it this way, but most people prefer this. But it's the same thing, actually it's the same thing. Just a set of integers mod p. Set of integers mod p. Good. That's what we call a finite field. So when you hear somebody talking of a finite field, that's what it means. Set of integers mod p. And it means that, of course, that set of integers would form a field. And we've known what it means for it to form a field. It means that it will be closed under addition and closed under multiplication. 2 should be associative under addition and associative under multiplication. 3 must have an inverse additive and an inverse multiplicative. Every element should have an additive inverse and a multiplicative inverse. And then every set, that set should have both additive identity, multiplicative identity. Then we talk about distributivity and the commutativity and so on. Of course, we'll look at that example of finite fields. Now, before that, we supposed to know what characteristic of field means. When you hear the term characteristic of a field, what does it mean? So what the characteristic of field means, it just means, can you get a positive element here? A positive element in the field, such that that positive element, if you multiply it by 1, the result will be 0. Can you get that element so that the product of that element and 1 would give you 0? That element, therefore, is what we call the characteristic of a field. Characteristic of a field. Of course, if that element is not there, then we say that that field has characteristic of 0. If it's not there, then we say its characteristic is 0. That element is not there. But it's very important, the definition that we've given. And we will see how to find characteristic of a field. We are saying, if you are to go through the elements of that field, can you obtain an element which, when multiplied by 1, gives you 0? Can you obtain that element? That element becomes the characteristic. And if that element is not there, then the characteristic of that field becomes 0. So for instance, I've given an example here. I've given an example that if you were to consider the rational numbers, or the real numbers, or even the complex numbers, I'm just considering elements 1, 2, 3, for instance, for a -1, -13, all those elements, for instance. I cannot see an element which, when multiplied by 1, will give me 0. For instance, this one, 1 times 1 will not be 0. 2 times 1 will not be 0. 3 times 1 will not be 0. -13 times 1 will not be 0. And therefore, these sets, of course, we say that there are fields also. These fields are of characteristic 0. Are of characteristic 0. Because we cannot identify any element inside here, which when we multiply by 1 gives you 0. Of course, that element should be non-zero. That element should be non-zero, should not be 0. Should not pick 0. You should not pick 0 and multiply by 1. That element should be non-zero. The element we are looking for. The element we are looking for should not be 0. Should be non-zero. So I cannot see any non-zero element here or here or here that if multiplied by 1, give me 0. But when you come back to the finite fields, it will be easier. For instance, let me consider this finite field. This finite field. No, this is supposed to be prime. Now, let me use the symbol I'll be using. The symbol I'll be using is this. I'll be using F most of the time to mean a field mod 5. Now, here I can, what are the elements here? The elements here are 0, 1, 2, 3, 4. Oh, those are the elements. So the question is, what is the characteristic of this? What's the characteristic of this? So what the question is saying, what element, when multiplied by 1, what element when multiplied by 1 gives you 0? Here. What non-zero element? What non-zero element? Here. Okay, I think this question I've done it below, so we'll go back to, we'll refer to, I've already done it somewhere. So when we reach there, so I don't want to again repeat it when that time comes. But that is how we are looking at it. How we are looking at it. What element will multiply by that? Yeah, this, I've done this question here. But before that, let me look at what a subfield is. We have a field, and then we have a subfield. A subfield is a subset of a field. And this subset of a field must be able to fulfill the properties of a field on its own. So you give it the properties of a field, it should be able to fulfill them, those axioms. So if it fulfills that, we say is a subfield. We are not saying that every subset of a field is a subfield. We are not saying that every subset of a field is a field. What we are saying is that only those subsets of a field that fulfill the axioms of a field, only those subsets that fulfill the axioms of a field become subfields. Not every subset will be a subfield, but only those that will fulfill the properties we looked at are the ones we refer to as subfields. Now, let's come to this example. It says, consider this ring, mod 5. Is a ring, consider it. Not ring, okay, it's a ring. So the question is, show that it's also a field. Show that it's also a field. So I want to show that this ring is also a field at the same time. Then after that, find its characteristic. Find its characteristic. In other words, find an element that you would multiply by 1 and get 0. That's what it means. So this question, I'm using it to answer so many questions. So the first question, I want us to show that it's a field. And the second question, I want us to get its characteristic. And the other question, I want to show that inside this field, if I took two elements, if I took an element here, an element A, and multiplied by x is an unknown. And if I get a result B, then this is the only result, that there can never be. Okay, if this product gives me B, then it means that X has only one value. X has only one value. So in other words, you can never get X to have two values. Like you cannot have X get the value of C and get the value of D at the same time. So X will have only one value. That's what I mean by show that AX equals to B has only a single solution. So you have those three questions that we want us to look at before you go to some applications. Of course, this question is just to assist us understand what a field is. Now, so for us to show there is a field, of course, going through all the properties, going through closure, and you can see our set had elements 0, 1, 2, 3, and then 4. So we want to check closure and addition and closure and multiplication. So let's take any two elements and sum them. 3 plus 4 will be 2. 3 plus 4 will be 2. And the 2 is a member of this set. 2 is a member of the set. So that means this set is closed under addition. Is closed under addition. What about 3 times 2? 3 times 2 will be 1. And 1 again is a member of this set. So I'm shown that this set is closed both under addition and multiplication. It's closed under the two operations. Associativity will be obvious. We don't need to bother ourselves with it. Even commutativity will be obvious. For instance, if you have 2 plus 3, the result will be the same as 3 plus 2, and this is 0. And again, if you have 2 times 3, The result is the same as 3 times 2, and this is 1 in both cases. Is 1 in both cases. So it means that this set is commutative under addition and commutative under multiplication. You can see that it has the identity element 0 here. Under addition, it has identity element. And under multiplication, there's also an identity element. Under multiplication, there's also an identity element. What about inverses? What about inverses? What is the inverse of 2? Under addition. Under addition, the inverse of 2 is 3. Because these two give us 0. So again, the inverse of 3 is 2. Under addition, the inverse of 4 is 1. Because this will give us 0, mod 5. Under addition, the inverse of 1 is 4. So every element has an inverse under addition. 2 has an inverse of 3. 3 has an inverse of 2. 4 has an inverse of 1, and 1 has an inverse of 4. Under addition. What about under multiplication? What is the inverse of 2? The inverse of 2 will be 3. Because this will give us 1. And again, that means the inverse of 3 is 2. What about the inverse of 4? Before itself. The inverse of 4 before itself, because 4 times 4 will be 1. And the inverse of 1 will be 1 itself. So every element has an inverse under addition and an inverse under multiplication. And I'll give you an example. So that's how you are doing to show that it's a field. You're going through the axioms of a field and showing that they are fulfilled, showing that they are satisfied under addition and satisfied under multiplication. So you can check the other axioms. So you checked closure, associativity, you checked commutativity. What remains is just distributivity. That's what remains. Can you check that? Sir. Yes. Yes.
Fields are different from rings.
Yes. Yes, they are different. The difference is at this point, we are considering the two operations at the same time. If you look at the axioms, if you look at the axioms of rings and the axioms of fields, that are different because when you look at the axiom of rings, for instance, we said that a ring, first of all, should be a commutative group. A commutative group. Then after that, you now come and look what the only time we're considering multiplication for the rings is under distributivity only. Under distributivity, you're now considering multiplication. But if for the other axioms of a ring, you're only considering the axioms of a group under addition. You only look at addition only. Addition, commutativity, look at addition. Closure, look at addition, and so on as you progress. But then you bring in multiplication only at the point of distributivity. So when you look at the axioms of rings and fields, they're very different. But you see, fields, We are considering the two operations at every axiom. Closure, consider the two operations, addition, multiplication. Come to associativity, consider the two operations. Check addition, check multiplication. Come to identity element, consider the two operations. Check the identity under addition, check the identity under multiplication. So that is our field, how we go for the field. But now come to the ring. Come to the ring. The ring, you begin by only focusing on addition. Focus on addition, addition, addition. Then when it comes to distributivity, that is now when this multiplication comes in. So you go through those axioms and you see that's where the difference comes. That is where the difference comes in. I don't know whether you've gotten my explanation. Is it okay?
Yes.
Yes, yes. Yeah, so but what about a group? A group, we said we consider it a group and addition. So at that point, there's no multiplication at all. There's no multiplication at all. So you're only looking at axioms and you're considering only addition. And then another group could be a group under multiplication. So if it's a group under multiplication, at that point, there's no consideration of addition. There's no addition. So you're only considering multiplication. Look at closure under multiplication. Look at associativity under multiplication. Look at the multiplicative inverse of every element, and look at multiplicative identity element. So that is how a group is done. So a group only considering as one sign only. So it's either group under addition or it's a group under multiplication. What about a ring? A ring, we're considering the two operations, but we begin with the operation of addition. And then multiplication comes in later under distributivity and so on. What about a field? We are considering the two operations from the start. From the start, the two operations begin. When you're looking at closure, check for closure and addition, check for closure and multiplication. When you go to associativity, check for associativity and addition, check for associativity and multiplication. When you go to commutativity, check for commutativity and addition, and then for multiplication. So you're considering all those signs, all those properties, and all the two signs as you move. Good. Now, so we have to look at the characteristic of Z5. So in other words, what element, when multiplied by 1, gives you 0? So in fact, it's easy how you get it. We're just asking ourselves, how many times are going to add this 1 itself to get 0? How many ones are you going to add to get 0? Maybe 5 of them. 5 of them. So then the characteristic becomes 5. Of course, you know what 5 is. You know what 5 is, mod 5. But now, when we are asked about characteristic, we just say it's 5. Just say it's 5. You don't reduce it mod 5. You don't reduce it mod 5. How are we to show? How are we to show that if A is multiplied by X, giving us B, then X has only one solution? How are we to show? For us to show this, you have to realize that since you're working with a field, A has an inverse. You have to realize that. Then multiply this inverse on both sides. When you multiply the inverse on both sides, this is what you get. And you know that the inverse of A times A is 1. So that gives you X on the left side. And on the right side, you remain with what you have. Remain with that. So you'll have shown that X has only one value. And of course, you obtain that one value. Good. Another question? Now, let's again show that show whether this is a field or not. Z6, of course, we said if it's ZP, it would be a field. What about if it's Zn? If it's ZP, it will also be it will always be a field. It will always be a field. What about Zn? Zn, where n is any number, n is not p, where n is not prime, where n is not prime. If this is prime, then it will always be a field. But if this is not prime, then at times could be a field, but not always. Not always. Like the case I have here is not a field. So that's what we want to show. We want to show that one or more of the axioms we discussed is not satisfied. I want to see which one is that. Which axiom is not satisfied? That's what we want to see. These are the elements of Z6. Closure will be satisfied under addition. Let me see. 4 plus 5 will be 3. And 3 is here. 4 times 5 would be 2. Of course, we are doing it mod 6. Would be 2, and 2 is here. So closure has no problem. Associativity has no problem. Identity element has no problem because we can see the identity element under addition, the identity element under multiplication, they both exist, has no problem. So we just want to check the inverses. If the elements have both additive inverses and multiplicative inverses. And of course, we know that if you have Zn, the elements which are not relatively prime to n would not have inverses. Elements which are not relatively prime to n would not have multiplicative inverses. Like this is not relatively prime to 6. I'm not expecting it to have an inverse. I'm not expecting it to have multiplicative inverse. Even this is not relatively prime to 6. Even this is not relatively prime to 6. Any element that is not relatively prime to 6, I don't expect it to have a multiplicative inverse. The only elements I expect to have multiplicative inverses are 5 and 1. But additive inverses, I have no problem with that. Each of these elements would have additive inverses. Each of them will have an additive inverse. For instance, the additive inverse of 2 is 4, because 2 plus 4 is 0. Gives us the identity. The additive inverse of 1 is 5. And the additive inverse of 5 is 1. I have no problem with that. The problem is multiplicative inverses. I cannot see an element which, when multiplied by 2, gives me 1. That element is not there under this among these elements, there is no one element that you can multiply by 2 to get 1. There's none. There is none. But you can see here, 1 has an inverse, 1 itself, because 1 times 1 will give me 1. 5 also has an inverse. And of course, it's itself. 5 times 5 would be 1. But 2 has no inverse. And 3 has no inverse. And 4 has no inverse. Elements which are not relatively prime to n would not have inverses. And therefore, because of that, this fails to be a field. And I'm still answering the question that he asked. He asked, how is it different from a ring? And we said that we're considering the 2 properties at every stage, the 2 operations at every point, considering them at every point. You've seen, when you consider those addition and multiplication under closure, they were fulfilled. It came to associativity, they were fulfilled. But when it comes to inverses, we only discovered that we got additive inverses, but multiplicative inverses were not there for some elements. Therefore, it fails to be a field. If you will be considering it to be a ring, it will have accepted to be a ring, because this condition would not have been checked under ring. Under ring, we would not have checked whether the elements have multiplicative inverses. We would not have checked that. We would only have come, multiplication will have come just at the bottom end when you're looking at distributivity. So it will have become a ring. This one will have been a ring. But you can see it's not a field. Now, I'd introduced prime fields. Now we want to look at them because these ones are very important to us in security. Prime fields are very important, and we are considering mod P, where P is a prime number. And you've just seen that we cannot consider it under any number that is not prime, because you can see in this case, when we tried a number that is not prime, it was never filled. It was never filled. It was never filled. Of course, I think all numbers that are not prime, it will never be filled. Even if you were to consider 9, for instance, Z9, again, it will not be a field. Consider Z9. It will not be a field because you're expecting that elements which are relatively prime, not relatively prime to 9, like 3, like 6, would not have inverses under multiplication. Would not have inverses, and therefore it will not be a field. Even Z12 will not be a field. Also have elements which are not relatively prime to 12, like 2, like 4, like 3, like 6, 8, 9. All these elements will not have inverses. But when you take off Z11, every element here is relatively prime to 11. Every element. Therefore, to be a field. To be a field. So we want to look at prime fields in details, and you know what they are. We know what they are. We don't even need to go through the definition. The same definition when you're talking about a prime field. Of course, it must be a field. It must be a field. It must fulfill all the properties of a field, and you can see closure under multiplication and addition must be fulfilled. Then you come to associativity and addition and multiplication. Then commutativity and addition and multiplication, distributivity, and so on. So that is what we call a prime field. So a prime field is just a finite field with p elements, where p is a prime number. The elements of this are 0, 1 up to p minus 1. And it must fulfill these axioms. It must fulfill these axioms. And of course, you are doing this mod p. So when you add, you're doing it mod p, and when you multiply, you are doing it mod p. Now look at this question. The field is consists of these elements with addition and multiplication. Oh, okay. So in fact, I wanted to ask whether it's a field. And of course, I've already said it's a field. I just wanted to ask, is it a field? So that you now show me that it's a field. And of course, I began by, of course, it will be a field because this is P. This is P, so it will be closed under addition. And you can see, pick any two elements, mod 5, 3 and 4 mod 5, the sum will be 2, which is a member of this set. What about their product? The product will be 2 again, which is a member of this field. So you consider the same elements, both properties, both operations, addition, then multiplication. What about inverses? Check whether every element has an additive inverse and at the same time a multiplicative inverse. Every element, check whether it has. Of course, it's easy. The inverse of 1 multiplicative inverse will be 1. What about the additive inverse? Will be 4. The additive inverse of 1 will be 4. Let's come to 2. The multiplicative inverse of 2 is 3, because 2 times 3 is 1. What about the additive inverse of 2? Additive inverse of 2 is 3, because 2 plus 3 is 0. Let's come to 3. The inverse multiplicative is 2, and the additive again is 2. What about 4? The multiplicative inverse of 4 is 4. What about the additive inverse is 1. So you check whether every element has an additive inverse and a multiplicative inverse at the same time. You check, and you've done that. Once these 3 conditions are satisfied, the rest are obvious. The rest, like associativity, are obvious. Commutativity are obvious. So you only want to check the inverses if they exist. But the rest will then be obvious. Characteristic of a field. Now we're talking about prime field. See what? The same thing. The same thing you're saying. Can you obtain an element in this field that when you multiply that element by 1 gives you 0? That is what we call characteristic. And of course, you already have looked at that concept and looked at an example. Okay. Now, prime fields are very important. Of course, the next topic will be looking at how they are applied, especially in security, to do extension. That you have a field, you have a finite field, and out of this finite field, you can come up with another field. You can come up with another field. And this other field is what we call an extension of the prime field. Because the prime field you had was Fp. And then out of this Fp, you've come up with an extension where now you have Fp raised to n, where this n is coming from a polynomial. And of course, you already know what polynomials are. Coming from a polynomial is a power of the degree of a polynomial. This is the degree of a polynomial. We already talked about degree of polynomials. And these extensions of prime fields are very important when it comes to security. That is what we'll be looking at in our next lesson on Thursday afternoon. Let's look at this example. The example is to construct the addition and multiplication table of prime fields. This is very easy. Construct the addition and the multiplication table. Let's begin by addition table. We know the elements here, 0, 1, 2, 3, all the way up to 12. Those are the elements. So we want to add all those elements. We make addition table. Those elements are here, 1, 2, 0, 1, 2, up to 12. Then again, this column, we put those elements. So just adding, for instance, 2 plus 2 will give us 4. Just adding 2 plus 6 give us 8. 2 plus 6 give us 8. Just adding 4 plus 8 give us 12. Just adding, very easy. What about 5 plus 9? 5 plus 9. We are doing it mod 13. 5 plus 9 will be 1. We are doing it mod 13. What about 6? 6 plus 12. 6 plus 12. That is supposed to be 18, of course. But we are doing it mod 13. So divide by 13 and write the remainder, which is 5. So making addition table is something easy. And of course, we say that once you know how we do it with the groups, it becomes easy because we just use the same knowledge to do with the rings and even with the fields. When it comes to multiplication and addition, it becomes very easy. What about multiplication table? If it were groups, we would remove this 0, for instance. If it's multiplication, we would remove the zeros because it cannot be a group if it has a 0. But if for fields, the 0 is there. Now we're just multiplying. For instance, 2 times 3 will be 6. We're doing it mod 13. 3 times 9 is 27. We are doing it mod 13. The remainder, therefore, is 1. 6 times 10. 6 times 10 is 60. But we are doing it mod 13. That gives you 8. Because 13 goes here, is it 5 times? No, not 5 times. 4 times, and you get 52. When you subtract, you have 8, the remainder. Okay, 9 times 5 will be 6. Because 9 times 5 will be 45. 45. We are doing it mod 13. Yes, 9 times that will be 45. And 13 goes here 3 times. Because of that 9, when you subtract, you have 6 as the remainder. So again, multiplication table is not difficult here. The only thing we note is that while multiplying this, we must remember that 0 is still there. Don't remove it. Don't remove it because it must be a group under addition. At the same time, it must be a group under, no, it must be a field. It must fulfill both additive properties and multiplicative. Now, this is a very good question that we need to write a program for, and I wrote a program, but now you try and do that. What does the question say? The question says that consider this field. This field is from the example above. There's the example we've been looking at. We've been considering F13. The question is, find the set of all x and y. Find the set of all x and y so that x squared plus y square would give you 1 plus 7 multiplied by x square plus y square. So find out what is x and what is y. So this kind of question becomes easy if you were to create a program and then you can do it. But without a program, it means you must form multiplication table for each of the elements. For each of the elements, check, for instance, if x is 1, its square will be 1. Okay, so x, what about x square? So because we need x square. And okay, y can also be 1. So if y is 1, what would be y square? Also be 1. Now, so x square plus y square will then be 1 plus 1, which is 2. This is x square plus y square will be 2. Now, will it be the same? Will it be the same as 1 plus that? So let's see. 1 plus 7, x square is 1. And y square is also 1. So this gives you 8. So you can see that for this case, when x is 1 and y is 1, this condition is not fulfilled. So it means x cannot be 1 and y be 1 at the same time. Because then the left side will be 2 and the right side will be 8. So you check all pairs that will satisfy that condition. So I did check, and this is what I got out. I got 1, x can be 0 and y can be 1. So if x is 0, then x square will be 0 and y square will be 1. So the sum of x square and y square will then be 1. Good. So what about the right-hand side? The right-hand side, 7, x square is 0. So this is 7 times 0 times y square, which is 1. Anything multiplied by 0 will be 0. So this right-hand side then becomes 1 plus 0, which is 1. So you can see the left side and the right side are equal. So it means one solution is that x can be 0, and y be 1. That's the first condition. The second condition, I said, x can also be 0 and y be 12. Y be 12. Let's see. If x is 0 and y is 12, x square will be 0 and y square will be 144. But we are doing this mod 13. When you do this mod 13, you get 1. You get 1. So what is x square plus y square will be 0 plus 1, which is 1. Let's come to the right-hand side and see. The right-hand side will then be 1 plus 7 multiplied by x square. X square is 0. And y square is 1. So this gives you 1. So if this, what I wrote here, all of them are the solutions. These are the solutions that I wrote. The possibilities of x and y that will give you, that will satisfy that equation. But I want to give you an assignment to write a program that will go through all this and give you all the solutions. Otherwise, without a program, then it's a lot of work. It's a lot of work because you can see when I tried 0 and you have to try 0 and 1, try 0 and 2, try 0 and 3, try 0 and 4, try 0 and 5, try 0 and 6, try 0 and 7, and 8, 0 and 9, 0 and 10, 0 and 11. Then 0 and 12, you find it accepts. 0 and 1 accepted, 0 and 12 accept. The rest you are trying and they were not accepting to fulfill that condition. Then you are done with 0. Because x could be 0, and then you try all other y values, all of them. Then come when x is 1. When x is 1, try again, 1 with the 0, 1 with the 2. But you can see at that point, I only found that 1 with the 0 will work. 1 with the 2 will not, 1 with the 3 will not, 1 with the 4 will not, 1 with the 5 will not, and so on. So if you're writing a program again, that is what the program should be doing. The program is going through all these values of x. So it tries x with all the y values. And if it finds a combination that fulfills, it picks that combination. Then it goes to x is equals to 2 and tries with all possible y's, 0, 1, 2, 3. So I found that when x is 2, you have these two combinations. X can be 2 and y is 4. X can also be 2 and y is 9. The rest will not work. So that is how the program is supposed to then work. Supposed to try x values. Just pick one x value, try all the y's. Once you are done, pick the next x and try all the y's. And once you are done, pick the next x and so on until you exhaust all the values of x. So when you do that, this becomes the solution. So that one is an assignment. You try and do that program. So that when you meet on Thursday, of course, Thursday will be a physical class, and you present that your findings. Thank you. Thank you for listening. Alex, is there Alex or an announcement? Okay, so let's end there. Then we meet on Thursday.